The first variant of the chi-squared test is really not a variant, is a differentiation that people make. Chi-square test can be referred to as tests of homogeneity or of independence. Now, what's the difference? Quite frankly, I'm not going to go into that in detail. Your textbook actually does talk about it, so you're welcome to have a look at it. But in here, just suffice to say that they differ with respect to two things. One is the approach, the perspective that we can take from each of these tests in terms of the conclusions. If the test turns out to be significant, what can we say? What is going to be different? There is a very slight, subtle difference between these two tests, which, however, does not really affect the conclusions, the clinical applications of the test. So that's one reason why it's really a differentiation which is not of great importance. Yeah, that's right. You may still be confused. Don't worry about that. All I'm saying is that you're going to see these two words in research papers. If you want, you can clarify those at the times, but it's not a really big deal. Okay. In fact, the two tests work exactly the same way. The numbers are the same. The chi-square statistic is the same. The p-value they generated is the same, and so on. The only thing technically that changes is which totals are supposed to be fixed and predetermined. Okay. So in our table, if we're doing an independence test, all that we're looking at in terms of fixing in advance is the overall total. Okay, so we have to decide how big the sample size is going to be altogether. However, if we're doing a homogeneity test, then we have to require that the sample size in each group has to be fixed in advance. Okay, so this precludes the idea, for instance, of trying to compare three groups which are maybe different according to some special characteristic that we are not going to look for, but that may simply occur in the sample. We cannot do that. We have to decide ahead of time how many we want in each sample. So in a way, this suggests that if we're doing a test of homogeneity, you should sample according to some kind of stratified structure, okay, because you want to have a fixed amount from each of the groups, each of the populations. Okay. However, again, I would say don't fret over the difference between them. It's not really a big deal. Yeah, relax and just keep that in the back of your mind and bring it to the front if it's really needed. Here is another variant of the chi-square test that is actually a little bit more interesting, although it's still not used very often. Okay, and this is the chi-square goodness of fit test. Now, this is not a test that tests how fit people are. Okay, it doesn't have anything to do with fitness, but it has something to do with how well things fit with each other. Okay, are they together in the way that they should be? Because this test actually compares the observed proportions in a group to certain specified numbers. So in this case, we're only looking at one sample, one group, and we're not actually comparing that group to another group. We're comparing that group to some predetermined expected numbers. So for instance, what we may have is a nominal variable with 4 possible values A, B, C, and D, and we may have an expectation that the proportions of those values are as given there, 15, 20, 30, and 35. And then we may ask, well, is that true? Are those numbers actually correct or reasonable in our population? So in that situation, we do a goodness of fit test. We collect data and we compare the observed frequencies with the expected ones. Okay. Now this is mostly a theoretical kind of test that is used mostly by theoreticians and epidemiologists and so on, but you will see it used in some situations in articles, so you be prepared to have to use it. Another variant of the chi-square test is the binomial test. Okay, now this is a very simple test. In a way, it's the simplest kind there is. It's just a yes or no test from a couple of different perspectives. So binomial test, what it does, it compares the proportion of occurrence of just one event, okay, to a specified number. So in a way, it's a goodness of fit test, but for something where we're only looking at one of the values. Okay, so what we have is, let's say we have one group only, and we're asking, well, what percentage of this group satisfies a certain condition, say it gets healed by a certain treatment, or engages in a certain kind of behavior, or whatever. Okay, so we may expect that that percentage, for instance, is 15. So we're going to collect data, we're going to test, is it true that the percentage of people who do that is 15%? In that case, we're going to use the binomial test. Because of the fact that this test is so simple, notice that we only have one number to compare it to, it is in fact possible to compute the p-value exactly. Remember that generally the chi-squared test requires an approximation or uses an approximation. In this case, it doesn't have to. Computations can be done in order to obtain the p-value exactly based on the information we have collected.